Good afternoon. My name is Kevin Hu, and today I'll be presenting my project titled Interactive Visualization of Global Urban Heat Island Patterns through Vegetation Temperature Correlation. This project was conducted under the mentorship of Dr. Kevin C. Urbanization is accelerating rapidly, and with it comes increased heat exposure in cities. Despite the severity of urban heat island effects, many city planners still lack the tools to visualize these trends and respond with data-driven strategies. This project aims to address that by creating an interactive global map using 1 kilometer resolution satellite data spanning from the years 2000 to 2024. By enabling users to explore urban environmental trends over 2.5 decades, the tool reveals persistent hotspots and helps support sustainable planning and climate adaptation. The core problem is that urban expansion often removes vegetation, replacing it with impervious surfaces like concrete, which traps more heat. To study this at scale, I built an interactive platform that combines satellite-derived vegetation indices and land surface temperature data. It visualizes global patterns at the monthly resolution and 1 kilometer granularity from 2000 to 2024. The tool reveals both spatial and temporal dynamics, showing where declines in vegetation are driving temperature spikes and aims to help shape future urban cooling interventions. The main goal was to quantify and visualize the relationship between greenness, measured by NDVI, and surface temperature across time and space. For this, I relied on NASA GIBS's Web Map Tile service, an interface that provides access to MODIS satellite imagery at high resolution. My workflow consisted of 5 major steps. First, I retrieved monthly NDVI and LST data for any selected country. This works for any country in the world. Then I pre-processed the data, masking cloud and water pixels, reprojecting and clipping to a common grid. Third, I paired corresponding NDVI and LST pixels. Fourth, I ran regression analysis to examine their relationship. Finally, I generated interactive outputs, hotspot maps, seasonal animations, and a reproducible code notebook for others to use or build upon. The link to that code notebook is in here, as you can see. Now, starting off, as already mentioned, I retrieved the Web Map Tile service from NASA GIBS. This service catalogs globally available raster layers, including the MODIS satellite products I used, specifically monthly land surface temperature and vegetation greenness data. Accessing the Web Map Tile service metadata allowed me to directly import these layers into my code in a format that's ready for map-based visualization. This table lists all the datasets I used across various time frames. The cloud-linked project file provides access to all source layers, and users can explore multiple day-night combinations and seasonal variations. These two images show what the process data looks like for the US in July 2024. On the left is the land surface temperature map, and on the right is NDVI. From visual inspection, we can see a strong inverse spatial relationship. Areas rich in vegetation are generally cooler. This relationship becomes more explicit when we zoom in on regional patterns. For instance, the Pacific Northwest and Appalachians show cooler temperatures where NDVI is high. Conversely, the desert Southwest is both dry and hot. Anomalies, such as the high Rockies, show low NDVI but also low temperatures, likely due to elevation, indicating the importance of controlling for topography. I also generated monthly animations. Here's one for 2024 in the United States, showing how temperature peaks in summer, declines through the fall. It clearly captures seasonal cycles and adds a time dimension to the static maps. Unfortunately, the video does not play on the PowerPoint, but in the code notebook, if you went there, by clicking on this button here, it would show you how the temperature of the US changes throughout these months is specified in the range. Again, this works for any country in the world by just changing the country in the parameter here. You can change it to any year in the range 2000 to 2024 in the year parameter here. And if you gave this the third parameter 3 months instead of 2, this would then show you how temperature changes over those 3 specific months, rather than showing it over all the months in the range. As of now, it's showing it for every single month between the range 1 and 12 of this animation. A similar logic is used for the NDVI monthly animation. Greenness will increase in spring, peak in midsummer, and then decline in fall. This complements the LST animation and helps us understand how vegetation and temperature interact dynamically across seasons. To quantify the relationship, I plotted NDVI versus LST for July 2024 by using the pixel pairs from the images. It has to do with RGB values and applied a linear regression. The R-squared value was about 0.54, meaning NDVI explained over half the variance in surface temperature at a pixel level. The slope suggests a cooling effect of about 2 degrees Celsius per 0.1 increase in NDVI. This confirms vegetation has a meaningful cooling role, though not the only factor. Topography and urban morphology also play parts. This was my first foray into real scientific research. I learned how to formulate a testable question, parse technical documentation, and validate results. I also experienced how programming isn't just a technical skill, it's a scientific instrument. From missing data handling to regression modeling, I saw how code can unlock new insights from raw satellite data. Finally, I would like to thank my mentor, Dr. Kevin C., for his guidance throughout this project. I also appreciate Professor Lynn Kominsky, Ms. Ariana Arista, and the full N3 team for enabling this opportunity. Thank you all for listening to my presentation.